Michele, or, well, let's thank the organizers, first of all, for the opportunity to speak here. So this talk will have more physics flavor, definitely less mathematical flavor than the previous one, so I apologize for that. There will be symmetries. There will not be categorical symmetries, but hopefully will still be of interest to you. This is based on some work in progress with Victor Godet and Amartya Singh that hopefully will appear soon. Okay, so this talk will be based on entanglement. So let me start by reminding you what is entanglement entropy. Entanglement entropy is a quantum information-based observable that we can express it in various ways, but we can say that it measures in a given quantum state, in a quantum system, how much the degrees of freedom on subsystem that I will call A are entangled with the rest of the system that I will call B. So the typical starting point, the typical presentation, especially if you have some system with a finite dimensional Hilbert space, is that we have some Hilbert space. This is some factorized form. So there is a Hilbert space for subsystem A and a Hilbert space for the rest. We consider, for instance, some pure state, this one here. The state doesn't have to be pure. It could also be a mixed state, and essentially things would go through. In fact, one could also consider some thermal state. And then, since we are interested in the physics of this subsystem A, for instance, we have in mind that we can only access the subsystem A with observations, then we don't have access to the full density matrix of the state, but only to the so-called reduced density matrix, which is the trace over B. And even when we started with a pure state, this density matrix in general is mixed. And then we compute the von Neumann entropy of this reduced density matrix. Now, this is a very interesting quantity. As I said, typically one starts in quantum mechanics or in spin chains. But it turns out that this object can be extended to quantum field theories. One requires some regularization because in general, when we go to from a finite dimensional Hilbert space to infinite dimensional Hilbert space, like in quantum field theory, there are some divergences that need to be regularized. And what typically people take as a subsystem A is some spatial subregion. So we imagine we have the quantum field theory on some space, and we consider some spatial subregion, like a disk or a ball on some region, and we want to compute this object here. So it's difficult to overestimate the application of these quantities to various branches of physics. And here I just want to flash a few applications in the context of quantum field theory. Of course, there's been in the literature a lot of applications to spin chains and many body systems. So this is more from the point of view of a high energy physicist like myself. So for instance, one can use this object to determine, and in some cases even to define central charges in CFT. This is a femoral expression of this entanglement entropy in 2 dimensions. If you have an interval of size L, then it's case like a logarithm of this size, and the coefficient is the central charge. One can use it to define a central charge in 3 dimensions. There is some non-universal term, the scale like L, and then there is a finite term, which is universal, and turns out to behave like a central charge for 3-dimensional CFTs. It has been useful to give proofs of C theorems. It means the fact that these quantities like C and F are monotonically decreasing along RG flows. And one can construct these proofs by using properties like strong subadditivity. These are some inequalities that entanglement entropy satisfies, and they are due to unitarity. It has been used to detect topological order by studying a refinement of this quantity that is called entanglement spectrum. And then there is a whole world of application of this quantity to holography. In holography, there is the famous Ryu-Takayama formula that tells us that we can compute this quantity, this entanglement entropy, in terms of the area of an extremal surface in ADS. And this has been applied to study physics of evaporating black holes, among the various things. Okay, so we have this quantity, and now suppose that we say a few more things about this system. In particular, suppose that the system has some symmetry. And in this talk, I will consider the simplest, or at least a simple case of a U1 symmetry, although things can be generalized. So there is some charge Q, there is this U1 symmetry, and I will assume that the charge actually factorizes into the sum of a charge that acts on A and a charge that acts on B. Now, if the state is symmetry invariant, that means that the initial pure state or mixed states commutes with Q, then it's easy to prove when you go to the reduced density matrix that this reduced density matrix is block diagonal, just blocks here and zeros outside. And these blocks corresponds to the charge eigenspaces. And this has led people to consider a refinement of this quantity that is called symmetry resolved entanglement entropy, because essentially you can just take a single block and you can compute the entanglement entropy of this single block. And so you have more data and you can study how the entanglement entropy behaves in the various blocks. So you construct this more refined quantity here. And for instance, just to give you an example of an application, if you have a CFT, in a two-dimensional CFT, and you study how this scales with the size of the system, now you can extract not just the Virasoro central charge, but also the Kac-Moody central charge with respect to this symmetry.
You have some assumption about the entanglement where the symmetry operator can like intersect with the entanglement surface in a topological way. So that you can define the QA and the QB separately.
Yes, so these definitions start their life in spin chains, where this is kind of obvious because so this charge is a local charge, so define its spins by spin. And then when you go to quantum field theory, things are less obvious. And I will put under the carpet all these details, as you will see in quantum field theories, in which you can you have a path integral definition of your theory, and you can compute things with a replica trick. We will see that things work nicely, but more in general, there might be subtleties, because we already know that this statement, strictly speaking, is not true. If the state factorizes, and then so everything is quantum field theory is a delicate issue. But as we will see, I will use the replica trick where things can be made precise.
So do you assume that the U1 is anomaly free or
I don't think so. I don't think so. Yes. So there will be no anomalies in my talk, but yeah, this is an interesting question, whether there is some. Could the anomaly be detected by this observable? I don't know the answer.
I'm not sure you'll be so easily able to split the charge up into charge of sectors A and B if you have an anomaly.
Well, in the quantum field, so we'll see. So in the quantum field theory setup, I think this will be possible. In the concept of spin chains, of course, there might be, I mean, if you have a vanilla system in which there is no anomaly, you can do it. Otherwise, there might be subtleties. So we'll see in the quantum field theory if it works or not.
Could you say again what you mean by Virasoro and Kac-Moody central charge?
Yes, so we are in a two-dimensional, if you are in a two-dimensional CFT, there is a Virasoro symmetry and there is a central charge. So this is the Virasoro that appears in the standard entanglement entropy. Now, if there is a U1 symmetry, where this is really U1, not just R, then there is a extension of the standard U1 Kac-Moody algebra that takes into account. So it's a extended chiral algebra that takes into account that really you have a U1. And then there is a well-defined central charge for that, which essentially is the anomaly of the U1.
What I find confusing is that I can have U1 symmetry, then I have U1 current, and I can build a stress tensor out of that, and that has a central charge, but that would just be the Virasoro central charge. I would get.
Well, it will be the Sugawara.
Yeah.
Yes.
How is that right? And you're saying these can be different in.
Well, the Sugawara central charge is different from the full central charge, right? It's that the central charge of the part of the theory that is coupled to the symmetry.
Oh, I see, I see. Okay, so that's like part of it. I see, but I see.
Yeah.
Okay.
Of course, it's not the only way in two dimensions. This is, in fact, let me say, okay, it goes perhaps beyond this component, but if you realize, so if you have some lattice system, and you know that, or maybe you don't know, you want to see in the infrared, does it flow to a fixed point? What are the properties? What is the central charge of this fixed point? So you have access to numerical computation, for instance, a spin chain. It turns out that computing these entanglement entropies is the most efficient way to determine the central charges. This is just a practical observation. Any other question? Okay. But what if the state is not symmetric? Okay, so suppose that now our reduced density matrix does not commute with the charge in the subsystem A, then in general, this reduced density matrix will not take a block diagonal form. I can still draw blocks, but all the blocks will be occupied. And then the idea that was put forward by these people was that we can construct by hand, and later on I will show you more slightly more elegant way how to do it. We can just put zeros in the blocks outside of the diagonal, so just keep the diagonal blocks, and then measure the difference between these two density matrices. Okay? So in particular, you compute the difference of the von Neumann entropies of these density matrices. So you compute this quantity here. This was named entanglement asymmetry by these people, because it turns out that this is a very good measure of how much the symmetry is broken in the initial state. Why it is a good measure? Because you can prove that it is semi-positive definite, and moreover, it is zero if and only if the charge commutes with this reduced density matrix. In other words, if and only if the reduced state is symmetry invariant. Yes.
It's obvious that, I mean, it doesn't seem obvious that this quantity is independent on the basis that it is.
What do you mean by the basis? I mean, the definition.
No, because you first put the zeros.
Okay, it's not obvious. And in fact, I mean, if you want this is the introduction, later I will show you a basis independent way. I mean, a very independent on anything way to define it. In practice, you do an average over the group.
I thought the basis of rho Q was whatever diagonal that you want. That's what you
Yes, yes. So in this sense, it's already clear, yes.
want. It is sort of determined by the U1.
Yeah, there is a very, yes. And anyway, as I said, this is the average over the group. Oh, expressed in that way, you don't even need to choose a basis. But we will see it. I will give more, slightly more details later on. Okay, so what is this good for? So let's flash some applications. So one nice application that was found in this very same paper is a quantum version of the so-called Pemba effect. So this is the effect by which hot water might freeze faster than cold water. So this very unintuitive phenomenon. But it was observed by Mbempa, which was a Tanzanian kid. He put boiled milk in a refrigerator, and he noticed, I can tell you more details about this story if you ask me. He put boiled milk in a refrigerator, and he noticed that when the milk was hot, it would freeze faster than if this milk was warm or cold. So this is a controversial phenomenon. It depends on a lot of details about the system, impurities. It's not very well understood, but these people find a quantum version of it in spin chains. So this is the plots that they find. And so if you take this delta S, this is the asymmetry as a measure of the breaking of the symmetry in some subsystem. So you see this red curve breaks the symmetry more than the green curve, and then they let the system relax, and the symmetry relaxes, the system relaxes, the symmetry is restored. However, the more you break the symmetry, the quicker this symmetry is restored. So this is an interesting effect that was observed. Also, you can use it, for instance, to detect the standard spontaneous symmetry breaking in the vacuum for a discrete symmetry. These people find this nice formula. So they find it, once again, in spin chains, but I believe that this is more generally valid in quantum field theories if the system is gapped in the infrared. So this is essentially the number of, you have some discrete symmetry, this is spontaneously broken, you have some number of vacua, this is the logarithm of the number of vacua that you get. And so this is detected by this quantity. Okay, and then there was some application to black holes, but it's not very relevant for me. So the goal of this talk will be to try to study this quantity, this entanglement asymmetry, in conformal field theories. And well, since we are in conformal field theories, well, I would like to study in conformal field theories and holography, although I will not have much to say about holography. Okay, since I want to study conformal field theory, I cannot just take the vacuum, because in a conformal field theory, there is no spontaneous symmetry breaking in the vacuum. So I have to pick up some less universal state. Of course, there are choices. And we selected a particular class of excited states, symmetry breaking states, that are natural from the point of view of holography. Maybe they are less natural from the point of view of field theory. I don't know. But anyway, we had to choose some class of states. And so here is the plan of the talk. First of all, I would like to come back to the definition of this quantity to give you some more details. Then I will tell you how to compute it using the replica method in quantum field theory. And then focusing on a particular class of coherent states and working perturbatively in some breaking of the symmetry, I was able to compute this quantity. We will be able to compute it. Then I will show you a different way to compute it, just a second, which is using relative entropy. So this will allow us to compute it in any CFT in various type of geometries. Then I will talk a little bit about the temporal evolution and this relaxation of this quantity. And then, if time permits, I will say a few things about holography, although they are not as exciting.
Considering the density matrix in a pure state or in a subensemble?
I will consider both, let's say, both a pure state and a thermal, sort of deformed thermal state. So we can do both. But it will be some specific classes of states. Because now that we are in excited states, of course, there are a lot of things we can do. Okay. So very good. So let me come back to the definition and let me try to be a little bit more precise. So I review what essentially what these people did. So we have a reduced density matrix. We have this local U1 charge that we assume can be written in this way. So now we want to construct what I will call a projected density matrix. So one way to do it is the following. So you take for each charge sector, you take the projector to that charge sector, and then you just sum over all possible charges. Okay, so this constructs this matrix in which you have only the diagonal blocks. Now, perhaps this is not super elegant. So another way to do it is that you take a Fourier representation of this projector. So here, so little q is just the charge, big Q is the operator, and you integrate over this parameter alpha, over the circle, which is the parameter of the U1. And then if you substitute here and you sum over Q, you get a delta function. So you end up with a single integral, and you have this expression here. So what is the expression? Well, essentially, this is our, okay, I'm not writing this A every time. So rho is this reduced density matrix on the subsystem. So you have this reduced density matrix, and you act with this unitary operator that acts on the Hilbert space and implement the symmetry. So you say this is the average over the group of this density matrix. So this is completely, well, the frontier is obviously this basis independent. Besides, this formula clearly generalizes to discrete groups. You just do a sum over the elements of a discrete group, and also to non-abelian Lie groups. You just do the integral of the R measure over the group with the R measure. Okay. Okay, very good. So now we want to construct this quantity here. So this will be the difference between the von Neumann entropies of this projected matrix and the full reduced density matrix, which is written in this way. And then if you want, you can notice that, okay, since here you're doing the projection on rho Q, here you can write rho Q or rho, it is the same because anyway you have the projectors here. So if here you write rho, you can write in this following way. And this is a quantity that has been defined and studied in quantum information theory. Is called relative entropy. Relative entropy is essentially a very good measure of the distance somehow, well, maybe that's not, well, not a distance, or the difference, say, between two density matrices. And in particular, as I said, on very general grounds, one can prove that this is semi-positive definite, and it is zero if and only if the two matrices are equal. So one can borrow known results from quantum information theory. Okay, so this turns out to be a very interesting quantity to measure symmetry breaking. So yes, this is what we will study. Okay, how do we compute it? So of course, this is not easy to compute for two reasons. Why we have to do one? So first of all, we have to do this projection of the reduced density matrix, and then if you want to compute this von Neumann entropy, you have to take a log of this matrix. This is difficult because this is an operator. So the one of the tricks, very common trick, is to first compute so-called Reni entropies or Reni asymmetries. So here the log is outside of the trace, so now it's not a problem. So essentially you have to compute the trace of some power of the density matrix. Here is the projected one, here's the unprojected one. And then we have to take a limit in which n goes to 1. Okay, so this gives the von Neumann entropy. So how do we compute these two things? Okay, so this is a standard quantity. This is the same one that appears in the computation of entanglement entropy. What about the projected one? Well, essentially, we insert many of these projectors, and so we obtain a formula in terms of charge moments. So you see there is a rho, there is an operator, there is a rho, there is an operator, a rho, and so on. And now you have to integrate over the parameters of these operators, and the only constraint is that the sum of the operator is 0. So there are n insertions, but there are n-1 parameters because the sum of the parameters is 0. And this will be important later on. So okay, so essentially you have to compute these charge moments here. These charge moments can be computed at least in two ways. One is to use, so essentially one way is to use the replica method. You can either replicate the geometry in which you compute these quantities. You can either replicate space-time, or you can replicate the theory, consider a theory which is the tensor product of many copies of your theory, and then study some twist fields. Okay, and here I will use the first method, but the second method could be used as well. Okay, so what do we have to do? So let me assume, so now it depends which state we are looking at. So let me assume that we want to study a state that can be prepared by some Euclidean path integral, okay, such that I can apply this method. So, so that means that this state, so I have some Euclidean path integral I'm in the Euclidean signature, in the lower half plane, I have some path integral, and then at t equal to 0, Euclidean time t equal to 0, I have some boundary conditions. This is the state. If I want a density matrix, I have two copies. So along, there is a cut along the real line with two different boundary conditions. And now when I take the trace over the rest of the subsystem, essentially here I glue the space-time and I'm left with a single cut in which there are different boundary conditions at the top and the bottom. And these boundary conditions corresponds to computing matrix elements of this density matrix. Okay? So this is a path integral realization of the matrix elements of my reduced density matrix. Now, if we want to compute the trace of rho to the n, the standard trick is that we take n copies of this spacetime. So there are these n copies, and they are glued together through the cut. So when you go from below to above through the cut, you go in the second copy, and then in the second copy, when you go from below to above, you go to the third copy, and from the last one, you go to the first one because it's a trace. Okay, so now you get just single geometry. You're supposed to compute the partition function on this geometry. I will call this geometry Rn. And then there is a normalization factor, which is just a partition function on a single copy to the power n. Okay? So this is the standard thing that you have to compute if you want to compute standard entanglement entropy. But now we want to compute the charge moments. Okay. So what we have to compute is something very similar, in which, however, when we go from the lower, when we go through the cut and we go to the second copy, we have the insertion of a topological symmetry defect. So if you want here, there is the connection with the theme of the conference, which is the exponential. So, okay, if you have a U1 symmetry, there's a current. The integral of the current gives a charge, at least if we are on the whole of space-time. And then here you have a parameter alpha that gives us the various operators that act on the Hilbert space. And these alphas are precisely this alpha over which at the end of the day we have to integrate. So the geometry that we have to study is one in which every time we go through the cut, there is this twist. And however, when we go back, the sum of the parameters of the twist is 0. Now, in general, if we have one of these topological operators and now we cut them, we can cut them such that there are endpoints or boundaries of them. In general, of course, the boundaries are not topological. Okay? They're only topological when they are closed. However, here the crucial point is precisely what I said, that the sum of the parameters is 0. And so since all these operators touch at these endpoints of the cut, at that point, we have these operators that come together. We have a junction. The parameters sum up to 0. And so this precisely condition such that they can, we have a good junction. And so the junction is topological. And so even though in isolation, this operator here will not be topological, in this particular setup, it is topological. And so I believe it is well defined. Does this make sense?
I thought you were going to consider states that break the symmetry.
Yes.
Not only the-
Yes, but this will be spontaneous breaking. So it will be the state that break the symmetry, not the theory. So the operators are still topological. It will be different if, because we could use this asymmetry to also study explicit breaking, because after all, it only depends on the state. The Hamiltonian never entered in any place. And in fact, it has been used in the literature to also study explicit breaking. In that case, the operators will not be topological. And in fact, there is a paper of Calabrese et al. In which they study these non-topological operators. And then the result, the answer depends on the dimension of the endpoints. There are some non-topological local operators. It's much more complicated. If you study spontaneous breaking, it's much simpler. Okay, so we end up with this formula. The denominator is the standard thing that we had here for the entanglement entropy. In the numerator, there is this new thing with the insertions, and you have to do this integral after all. So this gives the Renyi asymmetries, and then we take the limit n to 1, and we get the entanglement asymmetries. Very good. So now, as I said, we have to choose some states, because if we do it in the vacuum, we just get 0, because the vacuum in CFT does not break the symmetry. The one-point functions are 0. So we chose a class of states, that, as I said at the beginning, that are natural from the point of view of holography. And they are constructed in the following way. You take your Euclidean preparation of the state, and somewhere in the lower half plane, you choose, for instance, some collection of primaries, these BR primaries, and using some sources, some functions that are localized somewhere in the lower half Euclidean half plane, you turn them on in such a way that they break the symmetry, and so they prepare a state in which the symmetry is broken. These are natural from the point of view of the holography, because it's precisely the setup of holography. And so turning on this lambda just corresponds to turning on some boundary conditions for the scalar fields in the bulk that are dual to these operators. Okay, but we can study them in field theory. It's fine. Okay, I will call them some sort of coherent excited states. So in fact, just to make things easy, we simplify even further. So we take the case that there is a single primary V of charge 1, and then this lambda is just a delta function. So really, we insert an operator at a single point somewhere in the Euclidean space with some coefficient lambda. If you want, the only thing to notice is that so we do not insert a primary. If you insert a primary or given charge, then you have a state with fixed charge, and this will not break the symmetry. It will still be an eigenstate of charge. We take the exponential of a primary. So if you expand this, it will be 1 plus v squared, and so on. So this will be a state that doesn't have a definite charge. So it breaks the symmetry. Okay? And in fact, eventually we will work perturbatively in lambda. So in other words, we will only keep 1 plus v, essentially. Okay? But that is enough to break the symmetry. All right. So now, we have to compute the partition function in these replicated geometries in which we have many copies of this spacetime, Euclidean spacetime, and they are glued through the cut. And when you go through the cut, there are these topological operators inserted. So pictorially, you have the structure here. So this picture, in fact, is precise in 2 dimensions, is not precise in higher dimension. But pictorially, so this is one copy of spacetime, is the first copy. There are these 2 insertions. And then when you go through the cut, you go to the second copy. But at the cut, there is one of these topological operators, which coefficient alpha 1. Then you go to the third copy, where there is alpha 2. And when you come back, there is minus alpha 1, minus alpha 2, because the sum is 0. So pictorially, you have to compute the Euclidean path integral on this stuff. So how do we do it? So we'll do it perturbatively in lambda and leading order. So at each point, there is this exponential. So you can think that at each point, there is 1 plus v, 1 plus lambda v. And so you can choose, so at 0th order in lambda, you have all identities. First order in lambda, only one of them is v. Second order, you pick 2 of them, and so on. However, we still have charge conservation. So if we try to pick 2v, we get just 0 because it's not neutral, globally neutral. So we have to pick a v and a v dagger. So out of these solid dots, we have to pick 1, and out of these dots, this circle, we have to pick a v dagger. So now these topological operators come into play because we can take these topological operators and I can move them through the geometry such that it collapses on this one, and I can do the same for this one such that it collapses on this one. So I want to collapse all of them, and since the sum of the parameters is 0, then they disappear. Okay? As long as we are in the context of invertible symmetries. However, when they go through operators, you pick up a phase, and so you collect these phases, and the phase that you collect depends where the v was or where the v dagger was. And then you have to do this integral over the alpha, and what you discover if you do it is that actually in order to get something non-zero, you have to cancel the charge, not just in the sum of the geometries, but chamber by chamber. Okay? So what do you get? So in the denominator, there was just the full path integral. So when I expand, there is a 1. The first term is a 2-point function, v dagger, where v can be in any copy, which is this index j, and v dagger can be in any copy, and it is index k. And then I will have 4 insertions, 6 insertions, so on and so forth. But in the numerator, where we have this integral over alpha, the v and v dagger must live in the same sheet. So j must be the same. And now if you expand this, what you get is that actually this cancels the case in which j is equal to k. So the final result is that you have a leading order, you have to compute this 2-point function, but in which v and v dagger live in different sheets. Yes.
Does the result depend if you increase the number of replicas?
No, I mean, this is, so of course, so this sum goes up to n, but the fact that the integrals over alpha enforce the fact that you, in the numerator, you have to cancel the charge chamber by chamber, this is valid for any n.
If you would more than 3, maybe in the junction, you have some goodies on how to split the junction. Or
How to split the junction?
Usually you have equivalent
Well,
charges.
there is no charge. Let's see. So you're saying you might get some phase from some anomaly. But this phase, let's see. I mean, this phase will not depend on where you, I mean, which operators you pick here, right? So this phase, so I don't know what is the fate of this phase, but it will not affect the fact that you get this expression here. But okay.
So another question, will you always work perturbatively lambda and keep the linear order?
Yes, because I will work perturbatively lambda and keep the leading order. It turns out that this is the leading order.
So why did you started with this operator which is exponential and not just start with the operator which is 1 plus b?
Yes, you could, but first of all, because maybe afterwards you want to go to higher order and you want to see whether you can compute all the orders and resum. And then because, as I say, this is natural from the point of view of holography, because in holography, when you put this boundary condition, you insert e to the I lambda v, while, okay, if you want 1 plus lambda v, looks less nice. At this level is the same. Okay, okay, so we have this formula. And so now we have essentially to compute this, and you see this is a 2-point function, but it's still a 2-point function in a complicated geometry in which you have all these copies that are glued together. So let me start with two-dimensional CFTs. And in particular, let me start with the so-called Rindler geometry, in which the cut is a semi-infinite line. It starts at a point and goes to infinity. So then it turns out that the picture that I had before is precise because there is a conformal map from this geometry to this geometry. This conformal map is just the 1/n root. And so, so computing this 2-point function in a geometry in which you take n copies of these that are glued together is the same thing up to conformal factor as computing 2-point function in just flat space, which is this one here. So this is very simple. You can write it down, and here is the formula. So these are the Renyi symmetries. And here, for future references, I'm parameterizing these points where I have the insertion by the radius r, and this angle tau 0 that, okay, we choose in this particular way. So they appear in the formula. So now what we have to do is to take this formula and then do this sum for generic n, and then get analytic continuation in n and take the limit n to 1. However, this is not completely obvious, and in fact, I don't know how to do it in general. So what we were able to do was just for specific values of this delta, in particular when 2 delta is an integer. Okay, when 2 delta is an integer, here have some finite number of copies of sine, and then we use a Mellin transform of sine, some integral representation. And so here you have 2 delta copies of sine, so you have some number of integrals. So we were able to do for some specific cases like 1/2, 1, 3/2, and 2. We were able to do these integrals, and then once you do these integrals, you see that n appears analytically in the answer, and so then you can just take the limit n to 1. And here are the expression that we obtain for these entanglement asymmetries. Let me not comment now on them, because we'll comment some other cases in which there is a little nicer physics. Is it clear so far?
Remind me, who was delta?
So delta is the dimension, I didn't say actually, is the dimension of the primary operator that we use of this V, the primary operator that we use to break the symmetry.
You only ever get 2 insertions of this V?
At leading order, yes, only 2-point functions matter. Then the next order would be a 4-point function. So clearly, the leading order is particularly simple in this universe and these class of states because you only need to know about 2-point function.
You work with normalized correlators, right? So that if you
Yes.
put the unit, you get 1.
Yes, exactly. So you have, once again, you have to choose how you normalize the operators when you decide how you break the state, and we choose the standard normalization, which a 2-point function has a coefficient 1. All right, so as I said, we're using this formula here. We were not able to compute this quantity for generic values of delta. So let me tell you about a different method, which is based on relative entropy.
Sorry, where does lambda enter in the symmetry?
Lambda, so this S2 is the quadratic, or so if you want S is start lambda squared times this. So there is always a lambda squared in front that I'm not writing. Okay, so let's go back. So I already told you that this entanglement asymmetry can be written as a relative entropy between rho and the projected rho. And now let's specialize to the case at hand. So we are in this perturbative setup in which this reduced density matrix is essentially the reduced vacuum, okay, plus some perturbation, lambda, and then so on and so forth. But lambda has the properties, the property that it is V plus V dagger. And so in particular, once we project this rho, the vacuum is invariant and it remains there, but this one is completely killed because V has charge 1 and V dagger is charge -1, so there is nothing neutral. And so with some algebra, you can prove that this relative entropy is equal at leading order in lambda to another relative entropy between rho, the reduced density matrix, and the reduced vacuum. So this might look a bit strange because now it looks like the charge does not appear anymore in this formula, but this formula is correct. Okay. And now we can use, again, we can borrow some facts from quantum information theory where the quadratic expansion of relative entropy was studied. And it turns out that this is something that is called Fisher information. This is a metric in the space of density matrices. So you can see it as a metric around this sigma. And it turns out that there is a nice integral formula for it. This integral formula essentially comes from taking this expression here and using various integral representation, for instance, of the log, and you do a bit of algebra and you get this integral formula here. So this formula is general. However, now I want to specialize it to the following case. So you take sigma, okay, some density matrix. In this particular case is the reduction of the vacuum. And if you write it as e to the minus k, this defines the so-called modular Hamiltonian. Now, in general, this Hamiltonian is non-local, okay, because this is some horrible density matrix. However, if you are in a special case, and Rindler geometry is one of the special cases, in which, so there are a few special cases in which this modular Hamiltonian is local. It's a local integral of the stress tensor. The Rindler geometry is one of the special cases. Then this defines some geometric flow that is called modular flow. This is a flow in the Euclidean space. And in particular, in this Rindler geometry, in which you have the cut is a semi-infinite line, this flow is just a rotation around the end point of the cut. And so using this fact, you look at this formula, as you see that this sigma to some power is essentially angular evolution in Euclidean space. And then this delta rho corresponds to insertions of either V or V dagger. And so once again, you get that this trace is a two-point function. However, because of this S, which is the parameter that you integrate over, and this I, you have to do some analytic continuation in which you take one of the angles on this Euclidean space, and you do some analytic continuation of the angle, and you integrate. Okay? So you get some formula, which again is some manipulation of two-point functions, and so you can, you can try to compute it. Okay, so, you'd also do some change of contour. At the end of the day, you get some nice integral formula in which, in particular, let me stress, the advantage with respect to what I did before is that before there was this n, no? There was this Renyi asymmetries, depends on integer n. I have to analytically continue n, and here there is no n, it's just an integral. Okay? So this is good enough, I can compute it numerically. However, it turns out that I can also compute it analytically. It can be written in terms of some hypergeometric function. And okay, you get some curves. Okay. You can study these curves. For instance, they are finite. When tau 0 goes to 0, they diverge here. I don't want to discuss the physics here once again, because this is really the geometry for me is not very natural. I want to discuss some other geometry that is more interesting. Okay, but the point is that we can actually compute this entanglement asymmetry for generic values of delta.
What is epsilon?
Yeah, so it's some just contour prescription because there is a pole here, so you have to compute this integral.
But in general, this quantity doesn't depend on some cutoff of something, right? I mean,
No, so it does not depend on UV cutoff because entanglement entropy does in general. No, the leading term in entanglement entropy. Exactly. So now there are two rows. Again, if you have spontaneous breaking, the UV is the same. The details cancel. Okay, so can we compute other geometry? I mean, this Rindler geometry is not the most interesting one, perhaps. I don't know. And it turns out that since at leading perturbative order, and for our excited states, these asymmetries behave as two-point functions. So every time we can do a conformal transformation from the Rindler geometry to some other geometry, this allows us to compute entanglement asymmetry in some other geometry. We just have to keep track of conformal factors. Yeah, so if we have some map, then the two asymmetries are the same up to changing the variables and putting the suitable conformal factors in front. And if we are in 2 dimensions, in fact, all these conformal transformations are just holomorphic maps. So this is the same formula. So essentially, we can try to explore which other geometries we can access to. And there are some interesting geometries. In particular, we can do a finite interval as opposed to the semi-infinite line. We can do a finite interval at non-vanishing temperature. We can do a finite interval in finite volume. And then we can also do some quenches. So let me quickly show you what we can do. Yes.
Sorry, I got lost. Are you using some special property of conformal symmetry in Rindler spacetime to simplify? Or
So what I'm using that, so I have computed this quantity, and now just for the leading order, and for these particular states that are created by inserting two operators, I mean, one in the past, Euclidean past and Euclidean future, this behaves like a two-point function. So now I just do a conformal transformation, and I know how this transforms under conformal transformations. If I were to go and compute the next order, it would be a 4-point function. So now the second order, the order lambda to the fourth, will, I mean, I could still keep track of how it transformed, but it will be more complicated. And so you see that the full answer, if I was able to compute the full answer, would behave in a very complicated way, because each order will transform in a different way. So I don't know how the full function transforms, but at least if I work order by order in lambda, it's just conformal factors. Okay, so for instance, let me consider the single interval. So there is a conformal map, which is this very simple holomorphic function, from an interval of size 2L to this Rindler space in which you have the semi-infinite line. So you can compute this asymmetry for whatever, I mean, whatever location of these points are, you just map them and put this conformal factor in front. Now, it turns out that formulas simplify if you put these points symmetrically with respect to the cut. You don't have to, but the formula are simpler. So this is what we did. We called eta the distance of this point from the cut. And so you can write down some formula. This is the conformal factor. And this function here, as I said, is the hypergeometric function. And you just have to transform the parameters in a certain way. And so, for instance, you can study how does this asymmetry behave as I change the size of the cut. And you find, for instance, that it grows linearly with the size of the cut. Okay. Is this expected? Well, I don't know. At least it is expected that as you increase the size of the cut, it increases, because if you have a larger subsystem, you detect more breaking of the state. But okay, at this moment, I cannot comment on this linear behavior. Okay, and there are other things that we can do, like finite interval with the finite temperature, or a finite interval in finite space. So I'm out of time, so let's skip this. Let me also say that, in fact, I discussed the two-dimensional case, but it turns out that this works in any dimension, because in any dimension, you can always map. So you can always study this Rindler space in which your cut is a half space, and you always have a conformal map from a disk or ball to this Rindler. And so the formula is exactly the same in any dimension. Okay, so this generalizes to any dimension, and in fact, the dimension does not appear in any formula. Okay, and there are other things one can do. So let me instead describe this temporal evolution. So it turns out that we can use conformal maps now combined with analytic continuation also to discuss temporal evolution of this asymmetry. And so the idea is that we want to study a sort of quench. So at some time, we prepare this state, this excited state, in which there is symmetry breaking, and then we let it evolve with the standard Hamiltonian of the CFT, and we want to see what happens. And what we expect is that since we are in a system with infinite number of degrees of freedom, there should be relaxation. And so we would expect that the symmetry relaxes, the system relaxes to the ground state where the symmetry is recovered. And so we would like to see what happens. And the trick to do it is that you first compute your asymmetry in this slightly more general setup in which you move the cut vertically along Euclidean time. And since now you see that the system is no longer symmetric under reflection, this, strictly speaking, is not a density matrix. If you want, it's not Hermitian anymore. But you can do the computation, and afterwards, you analytically continue tau to IT. So now it's like this cut is moving, instead of moving vertically in Euclidean space, it's moving in some orthogonal direction, which is Lorentzian time. But now you see that it is symmetric under reflection. And in fact, if you write it, it is now Hermitian. And in fact, this is the time evolution of your density matrix. Yeah, so this allows you to compute the temporal evolution of this. And in particular, we can describe these quenches. So what do we get? So let me just study it for the case of the interval, where the insertion are symmetric, such that the formula are nicer. Okay, there is a nice formula, and now you can try to study it. So if you choose some values for delta, for this, which is the dimension of V, eta, which is how you prepare the state, and then you plot against time, you indeed see this nice relaxation. So this is what you would expect. You can try to see what changes if you change the size of the interval. And what you find is that the larger is the interval, the longest is the time that is required to restore the symmetry. And this is also physically expected. If you have a larger system, it takes longer to thermalize or to relax. And then, okay, you can also study with temperature, but okay, I didn't talk about temperature. On the other hand, you can ask, okay, what about if we study different out of equilibrium states? Can we compare how they relax in time? What are the different speeds? In particular, we can try to explore this question, whether states in which the symmetry is broken more can exhibit shorter relaxation time. And so what we did was to consider states that are prepared using operators of different dimension. There are many things one can do. So if we do that, we found these curves. And so this nicely reproduce this quantum version of the Mpemba effect. So states in which you use operator of a larger dimension, it turns out that it breaks initially the symmetry more, but then they relax faster. So they give this quantum version of this fact that perhaps hot water freezes faster than cold water. Okay, any questions so far?
One quick question. So the states that you use also break like translation invariants.
Yes, so this is, I call them local quenches.
Yeah. But so could you study this also for restoration of translation invariants instead of the U1 symmetry?
Perhaps in the sense that one could use, instead of a U1 charge, one could perhaps use the Hamiltonian as a charge. Yeah, I don't know. This is not. I mean, we discussed this in the past, but
Not factorize.
sorry.
For translation, the symmetry does not factorize. I mean, that's true. Like how important is this factorization property in the story?
Okay, so yes, it's not obvious how to do it, but yeah, I don't know what can be done or cannot be done. Okay, so I have just a few minutes. So let me just say a few things about holography. So the only thing I can tell you about holography is that if you use this formulation in terms of Fisher information, it turns out that there exists in the literature an integral formula for this Fisher information. In other words, if you have a state in which such that the modular Hamiltonian is geometrically realized, the modular Hamiltonian is local, the local integral of the stress tensor, and then you study a state that perturbatively breaks, a state which is perturbatively close to this vacuum, there exists an integral formula for this Fisher information that essentially compute the same thing. So since I'm out of time, I'm not going to explain what are all the ingredients in this formula. There is some integral formula. Since this is proven in general to be the same, okay, we computed it. Of course, we get the same, but okay, this is guaranteed by the theorem. Perhaps just one nice observation is that one can take then that integral formula and can manipulate it a bit, and one can put it in this form that I find suggestive. So one can write it as an integral in some surface in the bulk of the bulk current. So since the boundary here is a U1 symmetry, in the bulk there is a gauge U1 symmetry with a photon that couples to matter in the bulk, and so there is a bulk current, and it turns out that this asymmetry is measured by some integral of the bulk current. If you want, it's captured by the bulk charge, and you can also use the Maxwell equation to write it as some integral of the bulk field strength. At the moment, we don't have a clear explanation why this formula is correct, but I think it is suggestive. Just because, I mean, the ingredients that you would expect appear in this formula do appear in this formula, which is the bulk charge or bulk gauge field. Okay, so let me finish. I showed you this quantity, entanglement asymmetry, which is a nice quantum information-based observable to detect symmetry breaking, and we computed in various systems. So some natural questions. So to this audience, of course, can we generalize to categorical symmetries? The most obvious question. It's not completely trivial if the symmetry is not invertible. So I don't think that this is a stupid exercise. It could be interesting, but I don't know. And then, of course, I mean, one would like to go beyond these perturbative excited states. One would like to have some non-perturbative formula that is varied in general. And in this respect, holography might be an interesting playground. So it would be nice to have some nice holographic formula which is not perturbative, that allows us in a strongly coupled theory to compute this quantity. And then, okay, I didn't talk about black holes, but in general, I think there might be connection with black hole physics and the pitch curve and the islands and all this story. Okay, so thank you for your attention.
Thank you, Francesco, for the nice talk. And maybe time for one or two quick questions. If there are yes,
Could you just show the scaling form where you had this asymmetry scaling linearly with the system size? Could you?
Yes.
This is unbelievable. Much smaller, much bigger than eta.
Yes, so this is so this is, since this is a local quench, that is there is some length scale which is in Euclidean time, how much far there is from the cut disinsertion. There is a different behavior if you want, if the system is when the system is small with respect to the scale or when it's large.
a bit strange, right? Because it's kind of like you take your system, right? And you, I don't know, flip a spin or something, or break the symmetry just locally, and then an infinitesimal time after, your entanglement asymmetry already scales linearly with the subsystem size. Does it seem strange?
Yeah, I don't know. I'm not sure.
It feels like it violates locality or something.
This doesn't understand why you should violate
I
locality.
don't know. You flip a spin just locally,
Yes.
and then you find that your entanglement asymmetry scales with the size of your subsystem.
Yes.
I would expect it to scale as order one. In fact, one would perhaps expect an opposite limit for it to scale linearly without.
But I mean, this is Euclidean time. So I mean, you have some Euclidean insertion. And so this prepares a state that has some characteristic size, if you wish, which perhaps is over the eta. So already I mean, it's not just a local spin. I mean, already the system has some size, which is eta. Sorry?
Eta, not L.
Yes, but once again, I mean, since this is prepared in Euclidean, I mean, I don't have a causality that tells me that the break, in order to reach very far distances, I need some time, right? This is Euclidean prepared. It can instantly affect the whole of the whole line, and yeah, yeah. So, I mean, yeah. One thing.
If you take an OPE, right? You could somehow maybe move it towards the cut. Then it's even strange.
But I mean, this is computed from a 2-point function, so it's surely compatible with that. Yeah. The only explanation I can offer is that since this is Euclideanly prepared, I think that already your state at time 0 has asymmetry over the whole line. Then from there, there is time evolution. But at time 0, there is no time evolution, and already this asymmetry, although is focused around the region closest to the operator insertion, is already propagated everywhere. Once again, because it's Euclideanly prepared. But okay, maybe I can ask you more afterwards.
We're out of time, so we can thank Francesco for the next talk. We resume in half an hour.
Yeah,